Hi, my name is Hiba.
I'm Tori. And I'm Kathy.
And today we're going to be talking about our 6205 project called Raycasting.
So we created a raycasting engine that is able to render pseudo 3D worlds based on a 2D map representation.
And we're rendering 320 by 180 screens at 60 frames per second through HDMI.
Alright, so here we are in our pseudo 3D world, and you can see here that we have our top-down view of the world, and then we also have like our player position here. So this player position is controlled by the controller module, and so is orientation. So the controller updates kind of like, it has like up-down movement, and then also it has, we're able to rotate left and right. We're able to also kind of like allow for continuous pulling, so we're able to just kind of move forward, and then also we're able to kind of have more like smooth movements because we are communicating with the frame buffer. And then I also worked on like the ray calculations module, which is like the initial step of the ray casting logic. And what I do there is I just kind of take the position and orientation values, and from that position and orientation, I am like checking for every I'm calculating for every H count on the screen what the ray is in that direction, and then I'm sending that into the DDA FIFO, and the DDA is using this data.
So I worked on the DDA, or Digital Differential Analyzer, implementation part of this project, which takes the information from RayCalc and is able to calculate the corresponding line height, the precise location on the wall where each ray intersects, and the exact wall location that each ray and the screen intersects with. And it does this by taking incremental steps until it hits the closest X or Y wall, and then calculating distance away from this wall, and it ends up being inversely proportional to the wall height we want to render on the screen. And because the number of steps varies based on how far away the closest wall is, this module has a variable latency. So to account for this, we designed multiple DDA step FSMs to do the same type of calculation in parallel. And then this information is sent into a FIFO buffer.
So I worked on the transformation module and the frame buffer module. The transformation module essentially takes the vertical line data from the DDA module and determines the exact pixel value for each vertical line on the screen. And then this module sends the pixel data to the frame buffer module. The frame buffer module contains 2 frame buffers. One frame buffer stores the current frame, which is being rastered onto the screen, where the other is currently being populated with the freshly calculated pixel data from the upstream raycasting logic. So as you can see, as we're moving throughout this maze, there are different textures depending on what the map data is, and you can see this top level view of where the player is in pink as you move throughout the maze.
And we also have options to select between multiple mazes. We have up to 4 maps available. We can also represent a world grid up to 90 by 90. And we also decided to gamify this. So if you want,
You can find a pig
find a
or a dino. Wait, I saw the dino on the right. Wait, turn right.
You might be too good.
Oh.
There was one. It might be too hard. Where's the pig?